Okay, let's start with the big picture. System design isn't just about coding, it's a strategic approach to building large-scale applications. It's like designing a city. You need to think about everything from transportation and power to how different parts of the system interact. We'll be looking at scalability, reliability, performance, and how easy it is to keep things running smoothly. These are all really important considerations when tackling bigger projects. Okay, let's talk about designing systems that can handle lot of users and data. The first step is always understanding exactly what we're building for the specific needs and expectations. Then, we need to pinpoint where things might get slow or overloaded, those potential bottlenecks. We'll then choose the right architectural patterns, like spreading the load across many machines instead of just one, and prioritize statelessness so it's super easy to add more capacity as demand grows. Okay, let's talk about the building blocks of a distributed system. Think of it like this: you're not just running one computer anymore, you've got multiple nodes, which are essentially individual servers or machines working together. They need to be able to communicate, so robust network is absolutely essential. And how do they actually store all the data? That's where distributed storage systems come in, like databases designed for scalability. Then there's often a message queue, a way for services to talk to each other without being directly tied together, which helps with resilience. Load balancers are vital for spreading the load across your servers, and something like Zookeeper or Consul can help manage all of that complexity. Okay, let's talk about how we handle when things get busy, specifically scaling our systems. There are two main approaches: vertical scaling, which is like giving a single server more power, boosting its RAM and CPU, making it bigger. It's relatively straightforward to start with, but there's a limit to how much you can increase a single machine, and if that one server goes down, everything goes down with it. Then we have horizontal scaling. This is where we add more servers to the mix. Each handles some of the load, making our system more resilient because if one fails, others pick up the slack. It's often a better long-term solution, but can be a bit more complex to set up initially. Okay, let's talk about load balancing. It's a really important concept in building scalable systems. Think of it like this: you've got one server handling all the traffic to your website, and suddenly 1 million people try to visit it once. That's going to cause problems. Load balancing is essentially a smart way to spread that traffic across multiple servers so no single server gets overwhelmed. The load balancer sits in front of those servers and decides where each request should go, making sure everything runs smoothly. There are different ways it can do this, things like distributing requests evenly or choosing the fastest available server. It's a key component for ensuring your application stays responsive even under heavy demand. Okay, let's talk about CDN. They're a really important part of building fast and reliable websites. Imagine you have a website with lots of images and videos. If all those files are stored on just one server, people far away from that server will experience a noticeable delay when loading your site. A CDN solves this by distributing copies of your content across servers located around the world. These servers, called edge servers or POPs, store cached versions of your website's assets closer to where your users are. So, instead of everyone having to download everything from a single location, they get it from the nearest server. This dramatically reduces latency and makes for a much smoother experience. Let's talk about caching. Basically, it's a clever way to speed things up by storing the information we use most often in a faster place, like a temporary memory bank for your system. We have different strategies, such as writing data directly to both the cache and the original source, or waiting until later to write it back. It's also helpful to think about where you're caching from your browser all the way up to your database server. Okay, let's talk about database sharding. Basically, it's like dividing your huge database into smaller, more manageable chunks or shards. Think of it as splitting a really big book. Each shard contains a specific part of the data. These shards are stored on separate servers, which helps to distribute the workload and improve performance when you have a lot of users or a massive amount of data. You typically use sharding if your database is getting too large for a single server, or if you're experiencing really high reader-write traffic. It can also be useful if you need to serve users all over the world. You could shard by location to ensure they get fast access to relevant data. However, it's not without its challenges. Managing multiple shards and handling queries that span across them can add some complexity. Okay, let's talk about SQL versus NoSQL databases. They're really different beasts. SQL databases are like super organized spreadsheets with tables and relationships clearly defined. You use SQL to ask questions of this data, which is great for things like banking where you need absolute certainty that transactions are correct. NoSQL databases, on the other hand, are much more flexible. They store information in ways that resemble real-world objects, think documents or key-value pairs. This makes them really good for handling lots and lots of data quickly, which is why you might see them used by social media companies. Okay, so let's talk about message queues. Imagine you have two parts of your application that need to talk to each other. Maybe one handles user requests and the other processes them. A message queue is like a post office for those components. The first component sends a request the message to the queue, and the second component picks it up when it's ready. This keeps things separate, so if one part goes down, the other can keep running smoothly. It's super useful for making your system more reliable, scalable, and responsive, basically building a more robust application. Okay, so let's dive into eventual consistency. Basically, it's about how data is kept consistent across multiple servers in a system. Most of the time we want everything to be perfectly synchronized right away, like when you transfer money from your account, that should show up instantly everywhere. But building systems that do ** is really tough and slow. Eventual consistency says that if you update something, it will eventually become consistent across all the copies. Think of it like a shared Google Doc. Everyone might be editing at different times, but eventually everyone sees the same thing. It's great for things where small delays aren't a big deal, because it lets us build systems that are super reliable and can handle lots of users, even if it takes a little while for everything to catch up. Okay, let's talk about the CAP theorem. It's a really important concept in system design interviews, and honestly, it's all about trade-offs. Basically, when you're building distributed systems like many modern applications, you need to decide how you want to prioritize consistency, availability, and partition tolerance. The CAP theorem tells us that you can only realistically guarantee two of these at the same time. Consistency means everyone sees the same data, no stale reads. Availability means your system is always responsive, even if some parts are down. And partition tolerance is crucial. It's how the system keeps running when network problems occur and different pieces of the system can't talk to each other directly. It's a balancing act. You have to choose what matters most for your application. Okay, let's talk about the CAP theorem, a really important concept in system design. Basically, it tells us that when building distributed systems, you can only realistically guarantee 2 out of 3 key properties: consistency, availability, and partition tolerance. Consistency means everyone sees the same data at the same time. Think of banking transactions. Availability guarantees that your system keeps working, even if some parts are down, like a social media feed. And partition tolerance is all about keeping things running smoothly despite network problems. Choosing which two to prioritize depends entirely on what you're building and how it needs to behave. Okay, let's talk about data replication. It's a really important concept in system design. Basically, it means having multiple copies of your data spread out across different places. It's not just like making a backup. These replicas are constantly updated and kept synchronized. This gives you some serious advantages. First, if one server goes down, another can pick up the slack immediately, so you don't have downtime. Second, it protects against disasters. If your main region is hit by something bad, your data is still safe because it's being replicated elsewhere. Plus, reading data from a nearby replica can speed things up for users, and overall, it makes your data more durable. Let's talk about microservices. They are a really popular topic in system design interviews. Instead of building one huge application, the idea is to break things down into smaller, independent services. Each service handles a specific part of the overall functionality, like managing user logins or processing orders. This allows teams to work on different pieces independently, deploy updates without affecting everything else, and if one small part fails, it doesn't bring the whole system down. Okay, so let's talk about how monolithic microservices architectures stack up against each other. Think of a monolith as one big block. Everything lives together in a single codebase. When you want to make a change, you have to rebuild and redeploy the whole thing. Scaling can be tricky because you're scaling the entire application, even if only one part needs more resources. Microservices, on the other hand, are like a team of smaller independent services that work together. Each service does one specific job, making them much easier to scale independently and deploy separately. Because they are separate, if one fails, it doesn't necessarily bring down the whole system. Finally, microservices allow you to choose the best technology for each individual piece of your application. You don't have to stick with a single stack. Okay, so let's talk about API gateways. They're like the main entry point for all requests coming into your system, a sort of front door for your backend services. Basically, they sit between your clients and those individual microservices. Their job is to handle things like routing requests to the right service, making sure only authorized users can access resources, and even protecting your backend from being overwhelmed by limiting how many times someone can make a request. They can also transform data so that everything talks the same language. It's all about making your system more secure, scalable, and easier to manage in the long run. Okay, let's talk about rate limiting, a super important concept in system design. Basically, it's all about controlling how quickly users can make requests to your services. Think of it as a bouncer at a club, making sure things don't get too crowded and everyone gets a fair chance. We use tokens to track requests. Every time someone asks for something, they consume one token. If they run out, their requests are temporarily blocked. There are different ways to implement this, like the sliding window approach, where we look at recent activity, or using a token bucket which replenishes tokens over time. It's all about finding the right balance between keeping your system safe and not slowing things down too much. Okay, let's talk about building a system that's super reliable, something almost always available. The key is all about redundancy. Think of it like having backup systems in place at every level. We need to replicate our data using things like database replication or more advanced consensus algorithms. Then we use load balancers to spread the traffic across multiple servers, so if one crashes, others can pick up the slack. And crucially, we don't just have a single data center, we want multiple availability zones and potentially even different regions for disaster recovery. Automated failover is also super important, systems that automatically switch over when they detect an issue, without you having to manually intervene. Finally, constant monitoring and alerting are non-negotiable. It's about being proactive, not reactive. So, think about an e-commerce site, multiple web servers, replicated databases, and load balancers working together seamlessly. Now, let's move on to how we scale these things up when demand increases. Okay, let's talk about failover, basically how we make sure our systems keep running even if something hiccups up. Failover is all about automatically switching to a backup when the main thing fails. Imagine having a spare tire in your car. You hope you never need it, but it's there for when things go wrong. We use different strategies like planned switchovers, failbacks after recovery, and most importantly, automatic failover, where the system itself detects problems and switches over without us even noticing. Okay, let's talk about how we ensure our systems keep running even when disaster strikes. A really important part of system design is thinking about disaster recovery. There are a few common patterns we use. The most basic is backup and restore, just regularly copying everything up and having something to restore. Then you've got pilot light, which means keeping some critical services always running, ready to scale up when needed. Warm standby involves having a fully functional copy that's just waiting in the wings. Active/passive setups are even more involved, mirroring data constantly for instant failover. And finally, multi-region replication is about spreading your infrastructure across different areas, great for speed and resilience. Okay, let's think about how we build a URL shortening service like Bitly. The basic flow is pretty straightforward. Someone gives us a long URL, we create a shorter version and store that link. We then return the shortened URL to the user. To make this really robust and handle lots of traffic, we need to consider scalability from the start. We'd likely use a distributed database like Cassandra or DynamoDB to store our mappings between short keys and original URL. This allows us to spread the data across multiple servers if needed. Also, collision handling is important. While rare with good hashing algorithms, it's something we need to plan for. Finally, speed and reliability are key. Caching will be vital, and a CDN can help deliver static assets quickly. Okay, let's dive into designing a chat app that can really handle the load. First, we'll need to get users signed up and logged in using services like Firebase or Auth0 makes this much easier. Then comes the core part, real-time messaging. WebSockets are absolutely essential for pushing messages instantly to all connected clients. We'll store those messages in a database, probably something flexible like MongoDB or Cassandra that can easily handle lots of data. To keep track of who's online, we'll use Redis that lets us quickly check if a user is currently active. And crucially, as the app grows, we need to scale horizontally, adding more servers to handle the increased traffic. Load balancing will direct users to the available servers, and caching can speed things up by storing frequently accessed data. Okay, let's think about building a video streaming platform. It's a pretty complex system, but we can break it down. First off, we need to get the videos into *R system. That means handling uploads and then converting them into different formats for all sorts of devices. We'd use cloud storage like Amazon S3 or Google Cloud Storage to keep those videos safe and organized. Then comes transcoding, a service that actually changes the video files so they're suitable for different screen sizes and internet speeds. Once we have everything stored and encoded, a content delivery network, think of it as a bunch of servers spread around the world, is absolutely vital for delivering content quickly to users no matter where they are. We'll also need an API layer to manage all these requests from our user interface, plus authentication so people can log in securely. Finally, we'd use a playback engine to actually stream the video to the user and make sure it plays smoothly. Okay, let's talk about designing a ride-sharing app like Uber or Lyft. It's a really common interview question that tests your understanding of system architecture. The first thing to consider is the higher-level components. We need a user interface for both riders and drivers, a service to handle ride requests, a clever matching engine to connect them, and systems for managing drivers and processing payments. Crucially, scalability is key. We're talking about millions of users. We also need to think about how to track locations accurately in real time and make sure the whole system remains reliable even if things go wrong. That's fault tolerance. Okay, let's dive into designing a file storage service like Dropbox or Google Drive, a super common interview question. First off, we've got several key components: a client app for all the user interaction, a database to keep track of everything about each file, its name, size, who owns it, and when it was created. For this metadata, we'd likely use the NoSQL database because they can scale really well. Then there's object storage, where the actual files live. Amazon S3 or Google Cloud Storage are excellent choices here. Finally, the synchronization service, that's the magic that keeps things in sync across all devices. There are different strategies for how this works, like pushing changes to the server, pulling updates periodically, or a hybrid approach using change notifications. And of course, we need to think about scalability and reliability, which means replication, load balancing, and caching. Lots of techniques to make sure everything runs smoothly and doesn't go down. Okay, let's talk about designing a notification system. It's a super common interview question. The first thing you want to think about is scalability. We're talking millions of users here, so the system needs to handle that load gracefully. Reliability is also key. Notifications must get through. We often start with a queue like Kafka or RabbitMQ to buffer incoming requests, especially during peak times. Then notification processors, which might be separate microservices, take those messages and format them for delivery via push services, email, or SMS. Think about the different types of notifications you need to support and how each channel has its own requirements. It's a complex system, so always discuss trade-offs and consider things like eventual consistency. Okay, let's dive into idempotent API, a really important concept in system design. Essentially, an idempotent operation is one you can run multiple times without changing the outcome beyond the first time. Imagine updating someone's profile. Doing it twice has the same effect as doing it once. It's super helpful when clients are trying to retry requests because they don't have to worry about accidentally creating duplicate data or causing unintended consequences. Idempotency builds reliability and consistency into your systems, which is particularly important in environments where things can go wrong, like with network issues. So, always think about how you're designing your operations to be idempotent when possible. Okay, let's talk about data consistency, a really important topic when we're designing systems that spread across multiple services. Basically, it's about making sure everyone sees the same version of the truth. There are several ways to approach this. Eventual consistency is often used where you don't need asterisk immediate updates, like with social media likes, it'll eventually update everywhere. Strong consistency guarantees everything's synced at once, but it can slow things down and make the system less available if there are network problems. Causal consistency sits somewhere in between. If one event happens before another, everyone sees them in that order. It's a good balance. When you design, you have to think about how conflicts will be handled. What if two people try to update the same data at the same time? And, of course, you need to consider network partitions and understand the CAP theorem. It's all about making choices between consistency, availability, and partition tolerance. Let's talk about designing systems that need to respond quickly, real-time systems. These aren't your average apps, they're judged on how fast they react. Predictability is absolutely key here, meaning we want to avoid surprises and delays. Latency, which is the time it takes for something to happen and the system to respond, needs to be as low as possible. Jitter, that's variation in latency, should also be minimized for consistent performance. Resource management becomes really important. We need to make sure the most critical tasks always get the attention they deserve, often through careful scheduling algorithms. And of course, real-time systems have to be reliable and fault-tolerant, meaning they can handle errors without losing their ability to respond in time. Okay, let's talk about designing a rate limiter, a really important component in building robust systems. Rate limiters basically control how often users can access an endpoint to prevent overload or abuse. There are several algorithms you can use. The most common ones are the token bucket and leaky bucket methods, and there's also a simpler fixed window counter approach. Each has its strengths. The token bucket is great for handling bursts of traffic, while the leaky bucket helps smooth out requests and prevent build-up. Think about what your specific needs are to pick the right one. Okay, let's think about designing a search autocomplete feature. First, it's crucial to really understand the requirements. Are we looking for instant results, or can we tolerate a little delay? And where is our data coming from? We'll need a front-end to handle user input and display suggestions, a back-end service that processes searches, and of course, a place to store our data, like Elasticsearch or Redis. Scalability and latency are huge considerations, so we'll want to think about how to handle lots of users and keep those response times really fast. Okay, let's dive into designing a payment processing system, a really common interview question. At its core, it's about building a reliable and secure way for customers to pay. We start with the user interface where they initiate the transaction. Then comes the payment gateway, which is like a security guard handling sensitive data. The actual payment processing happens through a processor like Stripe or PayPal, who then interacts with banks to settle the funds. We break this down into different components: a customer interface, a secure gateway, a robust payment processor, and integrations with bank accounts. It's crucial that everything is scalable, so we might use microservices architecture for flexibility and redundancy. Having multiple servers and backup systems ensures high availability. Okay, let's talk about heartbeats in distributed systems. Think of them as little check-in reminders for your services. Basically, each service sends a small signal to another one every so often, like I'm still here. If the other service doesn't get that signal within a certain time, it assumes something went wrong and kicks off recovery procedures. It's a really important piece of the puzzle when you're building systems that need to be reliable, helping them handle failures gracefully. Okay, let's talk about leader election. It's a really important concept when you're designing distributed systems. Imagine you have multiple computers all trying to manage something together. Without a way for them to agree on who's in charge, things can quickly get messy. Leader election is the process of ensuring that one computer gets designated as the leader, and it takes over coordinating tasks and making important decisions. Algorithms like Paxos and Raft are commonly used to help computers reach this agreement safely. It's all about detecting failures, knowing when a computer isn't responding, and then electing a new leader if needed, while always making sure that only one computer is truly in charge at any given time. It's a vital part of keeping your distributed system running smoothly. Okay, let's think about how we design a logging and monitoring system for a really big service. First, you need to collect data from all the places it's generated your application code, database queries, even server events. We use collection agents like Fluent or Logstash to grab that data and send it along. Then, we need somewhere to store everything. Elasticsearch is a popular choice, but Splunk and cloud-based solutions are also great options. Finally, you want tools like Grafana or Kibana so you can actually look at the log, spot problems, track performance, and set up alerts when things go wrong. When designing, remember scalability. Make sure your system can handle a huge amount of data, and always think about redundancy to avoid losing important information. Okay, let's talk about managing configurations in distributed systems. It's a really important topic. The core idea is that when you have multiple services talking to each other spread across different environments, keeping everything synchronized and up to date becomes tricky. We need a central place to store our configuration, like a service we can all pull from, such as Console or Ept. It's super important to be able to update those configurations dynamically without having to restart the whole system. Think of it like rolling out changes smoothly. Version control is also key. We treat our config files just like code, so we track all the changes and can easily revert if something goes wrong. And finally, don't forget about environment-specific configs. Development, staging, production, they'll likely need different settings. Okay, let's talk about the circuit breaker pattern. It's a really handy tool for building resilient systems. Imagine you have several services that rely on each other. If one of those services suddenly goes down, it can trigger a domino effect and bring your whole application to a halt. The circuit breaker pattern helps prevent this. It essentially acts like a safety switch, stopping requests from being sent to a failing service where it detects too many errors. It then enters a testing phase to see if the service has recovered before allowing normal traffic again. This prevents you from getting stuck in an endless loop of retry attempts after a failure. Think of it as protecting your system from cascading failures, which is crucial for ensuring availability. Okay, let's talk about service discovery. It's a really important concept in microservices. Basically, when you have lots of independent services talking to each other, figuring out where those services * can get complicated fast. Without service discovery, you might hard-code IP addresses or rely on DNS, but that breaks down quickly as your system grows and changes. There are a few common approaches. Clients can pull a central registry, servers can register themselves, or you can use DNS for dynamic resolution. But no matter what, think about scalability, making sure things work even if services fail, and keeping those updates secure. Okay, so let's talk about some of the biggest headaches you'll encounter when designing distributed systems. It's not just about building a bunch of services, it's about making sure they work reliably together. One major challenge is keeping data consistent across all those nodes, which can be really tricky when things go wrong, like servers crashing or network problems. Then there's the always present issue of latency and bandwidth. Remember, no communication is ever truly instant. Finally, managing concurrent access to shared resources and ensuring transactions are atomic across multiple services require careful planning and well-chosen patterns. Let's talk about schema changes. They're a really common question in system design interviews, and for good reason. When you need to update your database structure while the application is running, you want to avoid any interruption. The key is minimizing downtime. Tools like Liquibase or Flyway are fantastic because they let you define your schema changes in code, meaning you can apply those updates without locking down the entire system. Feature flags are also super helpful. Think of them as switches that allow you to gradually roll out new features and columns to a portion of your users. This gives you time to monitor performance and catch any potential issues before they affect everyone. And, crucially, thorough testing in a staging environment is essential before applying anything to production. Okay, so when tackling a recommendation system question, it's really about understanding the data you're working with and then choosing an algorithm that fits. Think about where your information is coming from. User behavior is super important, as are details about the items themselves. Then, explore different algorithms like collaborative filtering, which compares users to find similar tastes, or content-based approaches that match items based on their characteristics. Finally, we need a way to measure how good our recommendations are, and A/B testing is your friend there. Let's quickly look at a simplified JavaScript example of how collaborative filtering might work. Okay, let's talk about handling data versioning. It's a really important concept in system design. Basically, you want to keep track of all the different versions of your data over time. Why? Because it makes things much more reliable and auditable. You can recreate past states if something goes wrong, track changes for compliance reasons, and even roll back to an earlier version if you need to. There are a few common approaches using database transactions to create snapshots, leveraging time series databases which handle this automatically, or utilizing object storage services with built-in versioning. And for event data, append-only logs can be really effective. The best approach depends on how much data you're dealing with and how often it changes, so think about those factors when making your decision. Okay, let's talk about designing a system for collecting and reporting metrics. It's a really important part of any scalable application. First things first, we need to define what actually matters. Don't just collect data randomly, think about the key performance indicators that align with your business goals. Things like service latency, how long requests are taking, error rates, and throughput are all excellent starting points. Then, you'll want a strategy for gathering this data, often through code directly in your application or leveraging logging tools or dedicated monitoring platforms. Storing it efficiently is key too. Time series databases are perfect for this kind of data. Finally, we need to visualize the information effectively using dashboards that make it easy to spot trends and potential problems. Okay, let's talk about how we handle security in a system that's spread out across multiple services. It's not as simple as just one login page anymore. You often need a combination of approaches like having a central place to manage user accounts and then letting individual services decide who can do what. We frequently use JWT, which are basically digital tokens carrying all the necessary information about the user and their permissions. OAuth 2.0 and OpenID Connect are also hugely important for allowing users to grant access without giving away their passwords. Think of an API gateway as a gatekeeper. It checks credentials before letting anything through. A hybrid approach is almost always best, balancing centralized management with decentralized service-level control. And don't forget about security best practices like validating inputs and limiting the number of requests from one user. Okay, let's talk about how we decide between synchronous and asynchronous processing. It's a really important question in system design. Synchronous is like waiting for someone to finish a simple task before moving on. It's great when you need an immediate answer or if there's a critical path that needs to happen first, like making sure resources are locked up properly. But it can slow things down if lots of people are asking questions at once. On the flip side, asynchronous is like sending a message and letting someone else handle it, perfect for when you need to manage many requests simultaneously, or if you have tasks that don't need an instant response. It's all about keeping your system scalable and responsive without getting bogged down in one long operation. Okay, let's talk about back pressure. It's a really important thing to understand when designing complex systems. Imagine you have a lot of requests flooding into your system, but one particular component can only handle so much at a time. That's back pressure in action. It's like a traffic jam where things start to slow down and potentially build up. We need strategies to deal with this. One way is rate limiting, essentially saying, okay, we can only accept X requests per second. Another good approach is using queues to buffer those spikes of activity, giving the slower components some breathing room. Circuit breakers are useful for preventing failures from cascading down the line, and retries with exponential backoff can help recover gracefully. Okay, let's talk about securing a distributed system. It's a big one. Distributed systems are complex beasts, and they present unique security challenges. The key is to think in layers. First, we need solid authentication, making sure everyone who connects is really who they say they are, using things like JWT or OAuth. Then, encrypt everything you can, both when data's moving around TLS and when it's sitting still. Don't forget network security. Firewalls and monitoring are critical to limit damage if something goes wrong. And absolutely never hardcode secrets. Use a dedicated secrets management system. Finally, constant monitoring and auditing helps you spot anything suspicious and ensures your systems stay secure over time. Thinking about the distributed nature of these systems means adding considerations like service meshes with MTLS, robust API gateways that can handle traffic and security, and ensuring data integrity across all replicas. Thank you for watching.